All right, everybody. I think this is as big as it's going to get, so I think I'll go ahead and get us started. My name is Frank Savina. I work for the Charles A. Dana Center. For those of you that don't know what the Dana Center is, it's actually a research center at the University of Texas at Austin. So our mission at the Dana Center is the idea of equity and access in math and science education. I'm a former math professor at a community college. I was in El Paso Community College for many years. I actually still live in El Paso, even though I live in Austin, which is 600 miles away, which in Texas is just around the corner. No, I'm just kidding. So I actually live in El Paso, and I work on curriculum for kind of gateway level courses. I work on everything from statistics to Path to Calc to quantitative reasoning. So that's kind of my job, and since I've been in the classroom for so long, my job also deals with professional learning. So I do a lot of professional development with teachers and professors mostly. Alongside me is Stuart Boersma, and I'll let him introduce himself just really quick, and then I'll get back to him in a little while. So if you want to share a little bit about what you do for the Dana Center, Stuart.
I'm from Central Washington University, so that's my real job is there. So I'm just a full-time professor of mathematics. Chaired the department for a handful of years. I've been teaching math at the college level for over 20 years. And I've been working with the Dana Center on and off for, I don't know, a dozen years.
I think there's another bus coming. I just
Oh,
want to
okay.
let you know, so I'll push people this way.
Sounds good. Thank you.
We'll
Appreciate it.
kind of talk slow for a little while.
Yeah.
So I've been working on and off with the Dana Center for quite a while. As they've worked on curriculum development projects, I've been invited to take place with that. So I've done some writing and lead authoring on the projects like the quantitative reasoning project, the Pathway to Calculus project. I did a little work with the Carnegie Foundation for the teaching when they were working on QuantWay. Back when Dana Center was also working on QuantWay at the same time. They were working together on that project. So yeah, I guess that's me.
Yeah, so the reason why I work with Stuart so closely is the Dana Center is split into four parts. We have a early childhood education kind of literacy component. We have a homeless education office as well, and then we have a K-12 component and a higher ed component. I'm on higher ed, so we're about 20 people. So we work with the field. We have to go out and grab professors whose day job is to actually be in the classroom to help us develop the curriculum. So that's why I get to work real closely with Stuart. So let me share a little bit about what I'm trying to accomplish with you all today. These are the four things that I thought we would talk about. And as we go through this, I'll have you guys talk. We'll have a discussion about some of the topics. But really, what I want you to walk away with is just kind of a national understanding of what pathways means. Math pathways. I've heard a lot of words about pathways today, but math pathways in general, I will focus on that. I want us to identify some opportunities to leverage math pathways to start to broaden participation in STEM, and I'll talk about that at kind of a scale, at kind of a institution level, and then start to think about how the partner disciplines play with us, right? As math departments. How is it that we interact with other departments to develop STEM fields? And then finally, actually get into some math, right? That's one of the reasons why I said, Stuart, you gotta come join me for a little while. He and I work on the content together, but he's our lead author, so I thought he would take the math part of it today. So that's kind of what I'm gonna try to do with you all today. So here's our vision at the Dana Center. We wanna ensure that all students have equitable access and equal opportunity for success in rigorous math pathways that are kind of aligned to their future aspirations and that lead to upward mobility in a sense, social and economic. These are the three things we want to do when we think about school, right? We want to prepare them to use their math and quantitative reasoning skills, both in their life and in their careers. We want to enable them to make timely progress towards their kind of certificate or degree. And then my favorite is the last one. As a curriculum developer, I want to empower them as math learners and as a mathematician. Right, so that's my favorite one right there. That's kind of our broad vision. So real quickly, I want you to take a moment to just kind of read this definition. This is what we mean when we say math pathway, okay? So just kind of take that in. And those sequences can be long, right? For engineering, they can be pretty long math sequences from, anywhere from college algebra through Cal 2, differential equations, linear algebra. And they can get longer if a student is underprepared, right? Because then you have to talk about the developmental piece. For other fields, it might be shorter. It might be one course. Maybe it's a quantitative reasoning course or a statistics course, right? So they can be short as well. So that's kind of a math pathway. So where do we come in, right? We kind of follow four principles. So my job as a curriculum developer at the Dana Center is to help institutions develop tools and resources that help them develop math pathways following these 4 principles. And the first 2 are structural. They're all about structure, right? It's about making sure students, regardless of college readiness, enter into a math pathway that's aligned to their field of study. That's what we want to do first and foremost. Second, we want them to complete their first college level math requirement within the first year. Okay? And that's where that can be done in many different ways, but we're in California, you all are doing CoreX. We're doing them in Texas as well. So this is where there's a big connection to the idea of core requisite courses, because we're seeing lots of data coming out that shows positive signs for those kinds of structures. The other 2 principles are kind of designed. They're kind of this idea of continuous improvement, right? So once you have those structures in place, then you start to think about the strategies you're using in the classroom to actually develop students as learners, and then integrating them across your institution, right? And then finally, the idea of using evidence-based pedagogy, right? That's where we come in. That's where Stuart and I work together to actually figure out how do we prepare students for calc? What does that take? How do students learn? Right? So when you look at the 4 principles, they look like this. It's the idea of quick structural change, right? The first 2, just structures. Right? Get some correct structures in there, align the courses, that kind of thing. And then starting to think about more carefully, how do we make these courses better? How do we tend to the pedagogy, et cetera? So in Texas, this is what we're starting to see. As you start to do this work, they start to align, we're starting to see this idea of meta majors. And I'll get back to meta majors in just a little bit, okay? You can see different pathways for students, right? Sure, you have a question? Sure.
When you say we or in Texas, I mean, and I think it applies system-wide, I mean, to community, to California as well, but you're talking about 4-year and community college system pathways, whether they're going into 4 years, but, you know, the dynamics are just, they change, they're different in the community college, but
We're talking 2 and 4 year, absolutely, yes. So it's critical, those transfer conversations are always critical, right? The conversations you're having between institutions is gonna be huge. So yeah, you know, part of the work that we do is I'm on the curriculum side, but we have policy people on our team that work to kind of smooth out that transfer, develop tools for different, for you know, advisors to use in state, stuff like that. So yeah, it's both 2 and 4 year. So this is what we're starting to see in Texas. And meta majors is kind of an important thing. I'll kind of get to how we develop meta majors, because there's a lot of local decisions to be made, right? We're not imposing on people. We're talking about 4 principles. So you can see social sciences, nursing going to stats, right? You can see the STEM pathway at the bottom. There's a teacher education and a business in Texas. And I'll get back to this in a little while. I just want you to kind of keep in mind that this is kind of a result of the 4 principles that we're talking about. We do work across the country, right? These are the states that we work in. Okay, California's in there. We are a service provider for the California state system in terms of CoreX. I'm not leading that work, but I know my colleagues are. I've worked in Texas and Washington with Stuart. I've done a lot of work in Missouri. So depending on the work that needs to be done in different states, we'll go out there and we'll work with states. And we work at the state level, right? So we'll work with task forces at the state level to work with community colleges throughout. So for example, in Texas, we worked with Texas Association of Community Colleges. They were kind of like a central hub for us, and then we worked with all faculty to start to develop the 4 principles. Broad-based support, especially from the math associations. MAA has endorsed this, AMATIC, AMS, ASA, which is statistics. Lots of policy institutions have supported us, APLU, ASCU, different policy organizations that really work on this have endorsed us. And we're starting to see it in policy, right? We're starting to see it in policy in lots of different states. So the question is, how are students doing when you start to do some of these ideas, right? Think about the 4 principles, the co-wrecking, the aligning, that kind of thing. And here's some starting data for us. You guys are probably aware with Statway, right? So you can see the Carnegie Math Pathways curriculums up there, Dana Center. Those were early efforts. We're already beyond that, even though I'm putting Dana Center up there. Those were initial efforts to kind of narrow down the developmental sequences by thinking about more appropriate content for preparing students. And our students were finishing their math class, their college level math class at 3 times their rate, right? But then after that came the state of Tennessee, And by the way, California had some amazing data come out, and I didn't add it to this because it was too new for me. But this is what Tennessee looks like. When you look at Tennessee, and you can see at the bottom here, those are all ACT scores. These are core reqs. Tennessee moved to core requisites as a state. So they're doing this at a large scale. And the data from Tennessee, as you look across here, you can see the ACT scores at the bottom. And you can see the percentages of them passing, right? Their first level math class, their first college level math class. And you can see that in the blue was before core requisites, in green is after core reqs. So across ACT scores, they're seeing huge gains in terms of students finishing their first level math class. This is community colleges only. Here's how they're doing in the four-year universities. Not as big, but still pretty big, right? So that's the idea of core requisites in one state. But the interesting thing about this data is Tennessee didn't only do core reqs, they also did math pathways, which means they were aligning, they were doing lots of things. So, one more, I forgot to talk about this. This is equity, this is still Tennessee. There's some equity here. Blue is before core reqs, yellow is full implementation of core reqs, and this is for minority students, right? So when you start to think about equity, you can see big jumps across ACT scores there as well. I was talking about the idea of comprehensive redesign, right? So the data you just saw happening in Tennessee, they weren't just doing core reqs. They were doing things like math pathways, core requisite courses. The idea, they're rethinking placement, right? They're thinking about multiple measures. They're using GPA. They're different things to place students. They're doing enhanced advising, and I'll talk more about that in just a little while. And they're developing those meta majors that I talked a little while ago, right? That's part of the alignment piece that goes with math pathways, okay? So that's kind of what's happening. That's kind of who we are. That's the work that we do. So then what about STEM? That's why we're here, right? So as we do this work at the Dana Center, one of the things that we think is that implementing multiple math pathways actually helps you broaden participation in STEM, okay? The question is, how, right? So what I want to do now is, if I can group you, if you're not grouped, can I have you sit with someone? Because I'm going to have you kind of chat, if that's okay. Yeah? I want to do this as a discussion kind of piece. So the first question I'm going to ask you here is, just kind of think about your institution for a moment, okay? Are you implementing math pathways? Maybe, maybe not. And if you're not, think about an institution or someone that you know that is actually doing math pathways, okay? And then, how is it going? So let's kind of start with that question, right? So if you'll kind of pair up with a partner and kind of talk that piece through. I can give you my PowerPoint afterwards.
That would be
Yeah.
fantastic.
Yeah. Sure.
I'm based in Seattle, and
Okay.
we are implementing MathPath, StatWave, QuantWave,
Thank you.
using the Carnegie model. And so this is always, it's good to build on what we have.
Perfect. I'll send you this right now as soon as we're done. Yeah? Hi, we're gonna have you come on in anywhere you like. But if I could have you sit with someone so you can kind of pair up, yeah? Okay. Thank you. Okay, that's fine.
I mean, you have very limited ways that you can enter into math now. Now there's 3 different ways. So you either start at the beginner level with a co-rec, you can go right into the one also with a co-rec, or if you can pass in to go right to your math course because they test out to either rolling out like and no, they are
Janet, should we go over a little bit or should we do it right on time?
get them through. So we've done kind of the initial co-rec between the next part of the plan.
We have one.
Oh, wait, I have it here. I was like thinking my backpack was still in the other room.
Yeah, so we're not sure yet.
Cool.
So, so we're supposed to go till 3:20.
Okay.
So it's only 2:38, and then 3:30 to 4 was,
Plenary. So you want me to be right at?
yeah, I probably need to end it pretty close to under.
Okay,
Yeah. Can you make that work?
I think so. Stuart, you want to chop some of your down? Yeah. All right, take 30 more seconds. 30 more seconds.
But we're just starting, so and I think if people go forward with it, I think it's helpful also in construction
All right, everybody, let me bring us back together real quick. Anybody want to share out how it's going? Are you doing math pathways and how is it going? Anybody want to share some of the things that surfaced for you all? No? Go ahead. Oh. Anybody? Nobody wants to share? This is a tiny... Go ahead, thank you. I appreciate that.
We followed your definition
Okay.
to make sure that we have.
Okay.
And so, for example, I was mentioning that at my school, we recently implemented statistics with prerequisites, so that our non-B-STEM majors could go into a class without algebra. We do have some barriers about transferring that still require intermediate algebra, but that's a different
Conversation.
And we also have StatWay, which I forgot to mention, but it's been running for 3 years at our school now.
Okay.
For STEM majors and business students, also we have STEM Core itself, but you could do the same set of courses for the second half of STEM Core. You could do them as one class or 1 and 2 or a combo together. So it gives students an option of how to approach the classes depending on their, like some people like learning 2 things at the same time, others don't like learning 2 things at the same time. So there is a pathway in that sense.
Okay.
But it's the same material.
Perfect. Yeah, it sounds like you guys are doing some good work. Yeah. Anybody else want to share what they're doing at your institution? Sure.
I am at Seattle Central College, Associate Dean of STEM, and we also have MathPath, StatWay, QuantWay as options for our students to go into. With MathPath, it's those students who are eligible to meet all of their pre-college math requirements within a quarter using ALEX. And that system is self-paced, so they can go as fast or as slow as they need. And they can, at the end of the quarter, they end up being transcripted with the course that they have reached the highest level of. So if they start at 87, Math 87, and they get all the way through Math 98, then that's what will be transcripted on their
transcript.
records. So
So
they
you-
have the option of completing all of their pre-college math. in a
Perfect.
quarter.
Great.
And they're only charged for one
Class.
course.
Okay. It sounds like, is that kind of an emporium model? It seems like,
Oh, yeah.
okay.
That
Alright.
works for so many of our students because it's that, when you think about barriers and equity and growth mindset, you know, if they're coming in at a pre-college level and then they're having to pay for all of these courses that will not be transferred or will go toward a degree, you know, it slows the process down tremendously. Even if they are awarded financial aid, it's being used up on courses that will not be
And their time, right? And their
in
time.
their time.
All right, so now I'll switch to a different question now. I want you to, again, think about this question is, when you think about your math pathways, are they aligned at scale? And scale is an interesting question here. It's an interesting word that I want you to think about, okay? I won't define it for you. I'll let you think about scale. So I want you to consider, are your math pathways aligned at scale? And how do you know? So if you kind of talk about that for a moment and see what comes up, okay? How would you know if you have scale?
We are trying to.
Face-to-face hybrid online and flexible is a combination of the hybrid. So, let me explain it. The students enroll in flex mode and the instructor is available as if the students can come in as they need to, but they're not required to come in. They can meet those requirements outside of class if they are able to. However, it's more of a bond that allows them to receive their if they need it. So it's very heterogeneous, such that the students who are enrolled don't all need the same differentiation or the exact same difference.
And you will find that students take advantage of that. Really, that's
As a
interesting.
matter of fact, we're growing it because the demand for it has increased. They absolutely know it. They absolutely know it. And Alex is also our placement.
All right. Take 30 more seconds.
One of the things that I think would address this question about skill is one of our placement tests that we are now advising. It went from being unproctored to proctored because those students who have some math skill were taking an increasing amount of time on the exam places versus they were scoring. However, once they came to the class, they were not permitted to. Yeah. And then those students who had little to none,
All right, start wrapping it up.
they were able to place themselves almost via Alex's expedite their time.
All right, let me bring us back together. So did you all think about scale? Anything interesting come up about scale? Like how would you know if you're actually doing alignment, right? If you're doing math pathways across your institution? What are your thoughts on that?
I think it's first of all, it's a challenge just to define and kind of think about it. So I really have to think about scale and then alignment in comparison to system-wide California. So I feel like, I'm in San Jose City College here in the Bay Area, so I think is our campus and the outcomes of our students align with, at scale with the rest of the system. And then we don't have structured pathways. I know we don't have structured, we have pathways, but it's not it's not part of a system-wide strategy in our institution or aligned with statewide guided pathways goal yet. We're moving that way. And so, we are not aligned yet.
I love the way that's it. That's what I wanted to surface a little bit is it's kind of a struggle to think about, right? And I agree with you that there's kind of two levels. As a state, how do you do that? That's going to take a lot of work, but I'll focus in on the institution for just a little while, and I'll try to make it as simple as I can from what I see working with different institutions, right? My wife happens to work for UTEP, the University of Texas at El Paso, and I asked her that question. I said, "Are you guys doing math pathways?" "Yes, we are. We're doing math pathways." What does that look like, right? Do you just offer 3 different pathways, but then everybody goes to one, right? I asked her that question. She said, "Well, what do you mean?" I said, "Well, I scanned your course catalog. There's a whole bunch of ORs in there. Why don't you all have a default math for each program of study?" And she looked at me like, "Oh." Because I would suspect that even though you offer different math classes, if you look at the data, right, if you look at your data and you start to think about meta majors, there should be some correlation between the math courses that students are enrolling in and the programs that they're taking, right? And I think that's the first part of the battle, is if you can start to think about, are we actually doing this or are we doing it in name only, right? Then you can start to think about how to do that at your institution, how to really create really nice pathways for your students, because in the end, that will open up the door for STEM. And Stuart will get to that in a little while, okay? So how do we begin to do that? Here's the next question I want you to think about. Okay? What role do other disciplines play in aligning the math pathways to programs of study? And that's maybe one place where you could start, right? What role do they play? I want you to talk about that, other disciplines, right? Your math. How do you interact with chem? How do you interact with psychology? What role do they play? Okay? So talk about that for just a little bit. I fly home on Sunday. I'm gonna hang around for a little while. Stuart and I, my nephew was supposed to be with me, so Stuart and I were gonna hang out with my nephew. But his mom got after me for taking him out of school too much. His mom being my sister-in-law.
Right.
And I was like, well, I gotta take him. And then he got sick, and she was like, he's done. He's not missing more school. And I'm like, all right, because he travels with me all the time.
Oh,
But anyway, so now I'm here with Stuart the rest of the weekend. So it'll be. What about you?
I go home tonight.
You go home tonight?
Yeah. Yeah, I've been here several times.
You've come here often, right?
What was that?
You do come here often.
Yeah, and last year I came here 2 or 3 times, but I don't ever see that much, but I don't know, sometime I should just rent a car and do it, but I don't know, I don't.
Just take it in a little. Well, it gets hard. When I travel a lot, I'm like, it's like travel, present, hotel, go home. It's like,
You just
but
wanted to do something different.
I did, and this guy's fun, so we'll have a good
Gonna
time.
go to the Winchester movie?
We are gonna go to the Winchester, yeah. Is that far from here?
I think it's about 28 minutes.
Yeah, it's
We're gonna try to get there.
between here and the airport.
Okay. Yeah, we're gonna have to roll.
Yeah.
However, I think it then
Usually it's new. They can come.
All right, take 30 more seconds.
Help us decide how.
All right. Wrap up your last thought. Whoa. Any thoughts? Any thoughts you all want to share in terms of programs of study? No?
Think about prerequisites.
Okay.
And so, number one is looking at the courses outside of the math department. And then across the campus and the disciplines and programs, what are the math advisories, prerequisites, and what is truly the math content or skill sets that the student needs for that course. So in our electricians program, the electricians are telling us that our students they need what we call Math 111 is beginning algebra, right? But the electricians teaching the course nor the math instructors have really gotten together to look at the course content in the textbook and that's really needed in math and see, do you really need everything in beginning algebra to enter that pathway? Otherwise, so what's happening, students are having to take beginning algebra, half of them fail. So they can't get into their pathway, then they fail it again, they repeat it, and maybe the third time they get it.
And worse yet, you don't know. You might not know if the content's actually meaningful for their career, right? And it becomes a compliance. I checked my box. I passed the course. Thank you for sharing that. Anybody else have something else to think about or to share? No. So on the previous slide, the idea was going to scale, like really thinking about default math, right? And really looking at your data to see if you're really sending the students where they're supposed to go. Here, the challenge is the conversation between the discipline and the math department, right? So one of the things that we want to think about is too often as math departments, we think of ourselves as a service discipline. Oh, we just serve them, they need calc, so it's the end of the discussion. They need whatever, and that's the end of the discussion. But the idea is how to engage the partner discipline, and it needs to be systematic. What I mean by that is, too often what we see is when the math department actually does try to engage, they'll go up and have a conversation around courses. What course would be good for your students? College algebra. Why? Right? So a systemic way to have this conversation is to say, okay, math department, take the lead. Think about learning outcomes. Let's start with that conversation first. Let's not talk about courses yet, right? So can we think about learning outcomes from all of our courses for a moment? So for example, that would mean, okay, go look at college algebra. The math department says, okay, let's narrow it down to five big objectives that are written in such a way that partner disciplines can actually consume what this means, right? Because often we write learning outcomes in a really strange way as mathematicians. So you do that let's say you offer 3 different courses, right? Take the 15 outcomes and mix them up and create a survey. It's that simple, right? Take that survey to your partner discipline and say, hey, I want you to think about this for a moment. I want you to think about which 5 of these, they're all mixed up, right? Which 5 of these are most important to you in your career, in your program, right? Then allowing some time to kind of consume that, let the department think through. Maybe they do it as a department together to reach consensus. So maybe all the psychology faculty sit down and say, hey, which are the 5 that we think are most important? Once they decide, provide that information to the math department. Then the math department can say, hey, it looks like statistics is for you. What do you think about that? Rather than just simply defaulting to, oh, we wanted college algebra. Yeah, but we didn't have a conversation around it. Now that we had a deeper conversation, maybe college algebra is not the course for you all, right? So really charging your math departments to take the lead. Really create that engagement. And a simple survey can go a long way, right? And then you can structure, you could even structure it where faculty can ask, like, what does this mean? Show me an example. Let's sit down and show me what you mean by this objective. What does it mean to use linear regression? Oh, I know how to use that kind of thing. Right? So if you're really doing the at-scale math pathways work, you have meta majors. You have conversations between the partner disciplines. It starts to look like this, okay? If you have, once you've talked through your departments and they figured out, okay, all of us want statistics, all of this other group wants calc, and this other group wants quantitative reasoning, you basically have 3 meta majors, right? This is a shift in advising now, because too often, it's the math that drives the choice of career. Too often, a student will walk up there and say, I'm just not good at math. Okay, you need to go over here. That's the wrong approach for students. Right? We begin by having a conversation around a broad meta major. What are your interests? Where do your interests lie? Let's not talk about math yet. What do you want to be? Right? Once you have the students select their meta major, then you say, hey, you need math. You chose social sciences, you need stats. Right? Then after that, you have the conversation about placement. Are you ready or not? Right? And if the student needs support, then you bring in your co-recs. So it's shifting the way you're driving students to their careers. Rather than letting math be the barrier, you're kind of opening it up here, right? And if you're doing co-recs great, then students, the idea of them jumping over works better. First and foremost, if they choose a meta major, when students change majors, they usually stay within that area, right? The whole point, that's why you want a default math class. You want that default math class because you know it'll serve the student even if they change, right? And if they happen to change across, like if they go from here to here, which happens very little across the country, it's like 4% of students or something, then they simply take a course. They don't have to go all the way back and take a long developmental sequence. They can take a bridge course or a co-rec course. So once you've done this, right, this is where the beauty happens. This is now students that truly are going to calc. Because if you think about pre-cal right now, if you think about college algebra right now, we have thrown everything at those courses. There's so many topics in there that may or may not prepare you for calc. This is where your math faculty can now say, let's think about this better. What are the topics we need here? What should this course look like? And more importantly, what should the pedagogy be? Right? Because we were talking about women leaving STEM. Why are they leaving STEM? Why are they not in these jobs? I think it has to do with pedagogy. There's something going on here that we can change, right? And that has nothing to do with content, okay? So the last piece is here, right? You start thinking about how to teach. You start thinking about the content. There's kind of two conversations happening. And what I want to do now is once you've kind of done the structural part, then I'm going to pass it over to Stuart here, who will talk about what that process of thinking about calc can look like, okay? Stu?
All right, so yeah, as Frank said, I want to talk a little bit more about the content that might go into preparing students for calculus. Or more importantly, actually, what I want to do is talk about a process that Frank and I kind of developed together with some other colleagues at the Dana Center, and we had lots of input from lots of faculty and mathematics educators from across the country to help us think about this issue of preparing students for calculus and what's the best thing we can do to get students ready to succeed in your everyday run-of-the-mill engineering calculus course. I'm not going to quote a bunch of data here. I think we've seen this morning. We've talked about it, and most of you are familiar with the basic fact that STEM occupations are growing. The supply, I guess, was the word that was used this morning by Rob, I think it was, is shrinking. Fewer college students are really, truly ready for college level mathematics, and hence aren't going to get prepared for the STEM professions that we know we need them for. And just that poor success rate in developmental math courses are really negatively impacting the number of STEM degrees that are awarded in a year. Okay, so that's the challenge. As Frank already mentioned, you develop math pathways, particularly at scale at your institution, and that does also open up an opportunity because you can now, if you want to focus on STEM, if the students who are in your STEM prep pathway, we'll call it, pre-calculus, I guess is what it used to be called, but I would maybe avoid that. Those students are there because they want to get ready for calculus. That's what they need for their science or technology or engineering or math degree. You don't have the social scientists in there, okay? We don't have the general college population in our pre-calculus class. I haven't actually taught pre-calculus in a while, but I remember the last time I taught it a few years ago, first day of class, 45 kids. How many people plan on taking calculus in the near future? Gosh, 5 kids will raise their hand. And it's like, why are you in a pre-calculus class? The whole point is that we're doing pre-calculus. So we can re-envision the pathway to calculus is what I would recommend. Let's get the right people there and let's give them the right content and the right structure and see what happens.
We have a bizarre, some degrees, like the sonography degree at TCC requires pre-calculus.
Yeah, when I was department chair, this gets back to, Frank was talking about to reach out to your partner disciplines. I think that's really important because some of those requirements I think are just artifacts from history long ago. Used to be college algebra, that turned into pre-calculus, and it's like that was like the entry college level course, and everyone should take a math class in college was, the thinking, which is not bad thinking, but that's probably not the right class. So I would recommend doing what Frank suggested and talk with those people and say, hey, your kids are in pre-calculus, that's great, but let's talk about learning outcomes. What is it you want them to get out of it? Do you want them to be able to identify rational roots of a polynomial? And if they look at you funny because they don't know what that means, it's like, well, maybe your student shouldn't be there either. And then we move on from there. I wouldn't be quite as combative as that. I mean, I tend to get a bit snarky. I'm sorry. I'll apologize in advance. Okay. How many people in this room are math faculty? A couple. How many are faculty from another discipline? Okay. And how about STEM professionals? Any STEM professional? We got one STEM professional in here? Okay. Frank talked a little bit about the role that some of the other partner disciplines at higher ed can help us out here. I'm kind of curious what we all think as faculty or STEM professionals that are in the room. How can the STEM professions help us think about content and structure and how to prepare students for calculus or for a STEM program?
I can use an example from the Merritt campus where we have our nutrition and dietetics family working with the math faculty to develop contextualized things that use ratios, conversions for that aspect of their math, so they see how it directly applies to their career education. And the math faculty essentially works with them to further the math competencies using domain, career items and terminology.
Great. So these partner disciplines or professionals can help us contextualize the mathematics, make it meaningful for the students as we teach it. Perfect. Other responses? What else can we get? Can we, I don't know, should we have conversations with the STEM professionals in terms of preparing students for calculus, or is this just a conversation that we have at the college level with academics?
Yes.
Yes.
I think we should have a
Yeah,
conversation with the
okay.
professionals, because just even in our roundtable lunch session, and even from the panel discussion, when the chancellor spoke about students completing their work, their programs of study without job placement, and that's usually tied into the path that we're doing in the academic world, not necessarily being aligned to the industry.
Yeah.
So I think it's very much so important to have the conversation with the STEM professionals so that we're on the right path.
Yeah, I was excited to be invited here because this is a very different type of conference than I typically go to. I tend to go to academic conferences, sometimes, most of the time, just math conferences, other math faculty, sometimes a little broader. But mixing in the professionals is really exciting here. I realize I have a lot to learn about the actual skills that are being required for maybe some of the jobs or the internships that have been talked about here. So I'm kind of excited to learn more about that. So a process that Frank and I worked on at the Dana Center, it's been, about 4 or 5 years now, I think. We wanted to think about both content and the architecture, the structure of courses in, say, pre-calculus course or a pre-calculus type of pathway. So in terms of content, we started, we utilized what we call, and probably a lot of other people call, just a back mapping process. We just sat down, again, with other math faculty across the country, and we had several kind of phone conversations, Skype conversations, and eventually a couple days of face-to-face brainstorming about what are the difficult ideas in calculus? Where do students struggle in calculus? Let's make a list of those. And then let's just focus on those ideas and ask ourselves, if we were to create a prerequisite course or set of courses from scratch, what could we do in those classes to better prepare students for those known hurdles that are coming up in calculus? And then also in terms of the architecture or the structure of the courses, we wanted to make sure that all the stuff that's been coming out in the last decade or so in terms of best practices, we would try to implement as much as possible. The active learning, meaningful experience, the idea of contextualized mathematics, which we talked about just a minute ago, giving students the opportunity and the support to struggle productively and to persevere as they move through challenging, open-ended problems. There were a couple hands when I asked about math faculty in the room. If you aren't a math faculty, how many people have taken calculus?
You aren't.
Okay. What's that?
If you aren't.
Yeah, if you aren't a math faculty. Okay, so even if you aren't teaching calculus, a lot of folks in the room have taken calculus. I don't know, what are the tough spots? What are the difficult ideas?
Infinity and limits.
Okay, the idea of infinity, the notion of limits. What else comes up? Too long ago to remember? How about people that are teaching calculus?
Deltas.
Epsilons and deltas? Okay.
But that goes back to the idea of
Okay.
infinity and infinitesimals.
Okay, okay.
The procedural stuff.
Big ideas, obviously, no pun intended. Yeah, okay. What else? Where do students struggle?
My experience with the struggle is when we go from what seems to have been computational math into analytical math.
Can you say a little more there?
So, for example, if we talk about series, students are used to compute stuff. So even though if we're talking about integrals, then they get a sort of like stepwise things to do.
Mm-hmm.
But then when we're analyzing series, that goes away.
Right.
That's not there anymore. You have a list of things that you can do, but there is no official.
Right, you're starting to move to the idea of argument, making a coherent argument.
Right.
You're not told exactly what tool to use at what time. You have the toolbox, and you have to kind of pick the right ones out and assemble them in the right order to be able to make some argument that your series is going to converge or diverge.
Which is
Okay.
more of what
Yeah.
math is instead of a procedural thing.
Yeah.
It's more of a,
Okay, so you got this tension between the procedural fluency, the drill and kill type of skills that are necessary, and then some of the big ideas, the big conceptual ideas. Right? I'll just put up a list of, this is stuff that you sit down with some math faculty, and lists like this are the ones that tend to come up on where students struggle in calculus. Limits are on there, which was mentioned. Okay, algebra comes up a lot. People always seem to complain about their students not knowing algebra, and then some of the big conceptual ideas certainly come up quite a bit. After working on this for a while, we came up with 4 overarching principles that we thought were necessary to implement in any sort of a pathway to prepare students for success in calculus. We wanted students to develop a deep understanding of the function process. This is to be contrasted with the action view of a function. I'll say a little bit more about that in a little while. The ability to apply covariational reasoning. There's research out there that tells us that a lot of students have a hard time keeping 2 covarying quantities in their mind at the same time. If you can't do that, preparing for calculus or succeeding in calculus must really be a struggle, because calculus is all about developing the language and the tools to describe change, to describe rates of change, or to add up lots and lots of small changes in various quantities. So I think it's really important that we could spend time developing students' ability to deepen their understanding or ability to apply covariational reasoning. Communication about functions, using function notation, and coming back to this idea of making the math meaningful as much as possible. Immediately meaningful. Yeah, you can go into class and say, okay, we're going to study all this algebraic manipulation, because when you take Calc 2 and 1, 2, 3, maybe 3, 4 classes down the road, there's going to be a day and a half where you have to know how to do this. Okay? That's not making things meaningful. Okay? So trying to let some of the we talked about contextualizing mathematics, bringing those contexts into the classroom, let the contexts, the obvious kind of important questions from the context, drive the need to develop the algebra, is what we tried to do. Okay? Not necessarily easy to do, but we tried every single lesson to open up with some kind of a meaningful problem that the algebra, or whatever the idea was we were going to discover that day, came about from, the context drove the need to develop the algebra. I think I'm going to skip a little bit of this. I want to talk a little bit about the process view of a function versus the action view of a function. So the idea of functions or modeling, often when we talk about mathematical models, we're using functions to do that modeling. And so students' ability to understand what functions are and to be able to use the language and notation is really important in terms of understanding what's going on in the calculus classroom. Research has shown, and a lot of my references are going back to the work of Marilyn Carlson and Michael Ortman and others. And there'll be an occasional reference up here, although please contact me or Frank if you want a bigger list.
But these are certainly not my ideas. This is not my research. But there is research out there that shows that a lot of students encounter with functions that they see functions as being static objects. All they do with functions are evaluated at a point. What's f of 1? What's f of 2? What's f of x plus h? What's f of h? I mean, that's kind of what they get out of functions. Everything is happening at a point. It's all just evaluating stuff. As opposed to the process view of a function, that's where students realize the deeper meaning of functions, and that these are processes. These are processes that can be composed with one another. They can be inverted. We can talk about inverse processes. They take on not just one value, they take on lots of value. They take on entire continuums of values, all right? And produces a continuum of output values. And so functions can really be studied by examining the behavior of input versus output. This also goes back a little bit to the idea of covariational reasoning. And functions are used to model dynamic situations, situations that are changing. We need the notation and the language of functions if we want to talk about measuring and describing change. Some of the research by Marilyn Carlson and Michael Ortman show that students who fail to develop this process view of a function have trouble in certain areas of mathematics. These certain areas of mathematics seems to overlap pretty nicely with where students are failing in calculus. So I put up a few things here, but a lot of the algebraic issues that people say, oh, students aren't understanding the algebra, they're not doing the algebra, they're failing at the algebra. A lot of that can go back to the fact that they just haven't developed the idea of this process view of a function very well.
Another question. Sometimes I don't know how to describe to a student that there's an analytical view of a function that preserves all of its components as things you can modify, vary, translate, and interact with. I'm not even sure what the language is that would let somebody who sees it as a single point of evaluation know that there's another door.
Mm-hmm.
Are there any suggestions or guidance for?
Yeah, and I'll get to that. And maybe I know we got started late here, so we're running a little bit short on time. I could show you some examples from at least the curriculum that we developed and how to get students to think about it. But the idea is, well, yeah, I'll get to that in just a minute. That's a good question. So ability to use functions effectively in word problems, not understanding what graphs of functions are really telling you. Again, students that haven't developed that deeper idea of a process view of a function tend to see these graphs as being static as opposed to really giving you a relationship between how one quantity varies with respect to another. And I'm just going to buzz along here a little bit. I talked a little bit about covariational reasoning. This is the ability to be able to consider how one variable changes with respect to another variable. This is really the central idea behind calculus. So if it's been a while since you had calculus, this is what at least the first 8 or 10 weeks of calculus is pretty much all about. But you can start this process early. In the early pre-calculus stages, students can still describe how one variable changes with respect to the other without having to necessarily develop the idea of limits or derivatives. The same researchers that I've mentioned a couple of times, they talk about 5 levels of covariational reasoning, and they were measuring students, I guess, measurement across these 5 levels. What I like about these 5 levels of covariational reasoning, and this will go back to the question from, I think it was that Courtney, had earlier in terms of how do you develop curriculum to take all this stuff into account. I use these 5 levels as a way to design curriculum. Right? So, early in a course, in a pre-calculus course or a pre-calculus STEM pathway, getting students just to recognize that one variable depends on another. Do that early. All right? And then, slowly progressing from there, identifying the direction of change. Okay, so this quantity is changing. Is it getting larger? Is it getting smaller? How much is it getting larger? By how much is it getting smaller? What's the average rate of change? Maybe, and then you get to the idea that these ideas of average rates of change might depend on which intervals you are studying. And this gets to the idea that average rates of change really are changes in and of themselves, and it slowly leads up to the idea of instantaneous rate of change and derivatives and yada, yada, yada. But essentially, you could just go down this bullet list, and as you're writing curriculum, make sure all this stuff is kind of built in. Maybe more of the earlier bullets at the early part of the course, and then make sure you're hitting all these bullets, just spiraling through and hitting these over and over and over again throughout your entire course. Often when I open up a traditional pre-calculus book and start flipping through the types of exercises that they're having the students go through, I'm seeing very little of this going on. And so it's no surprise that students are not developing this covariational reasoning skill. There's a question. Yeah?
Yes, I would also propose to math faculty and even any type of math that you are a specialist in, from an administrator perspective, which would be mine, and having interactions are very frequent interfacing with students, faculty, as well as potential faculty who are up for hire, tenure track faculty. It is incumbent, I believe, on the instructors as they're interacting with the students who come into the classes with different levels of math comfortability, is to really contextualize. I think that that's something from the conversations I have with students very regularly. That is one of the key themes or nodes that I've gotten from the conversations, from the public teaching demonstrations during interviews with potential faculty, is the key. And I think it's also important to have faculty, current faculty, at the table and in the conversations as well. But contextualization is something that helps it to stick. You know, especially when you're going through the foundational, the calculus, and even the advanced math. If they can contextualize it, that from my interactions with each of these groups, it's been very beneficial and I think advantageous.
So that's
to
come up
all.
twice now, and yes, definitely, I would.
I see the bullets.
Yep,
but
I would say,
contextualizing
yeah, I would
is
say
important.
rah. Definitely contextualizing is super important. You also mentioned the idea of access a little bit, engagement and access, and I would encourage people to think about, you know, their struggling students, you know, maybe the C students, think about what you do on the first 5 minutes of class on certain days. You know, maybe you're a third of the way through your class or halfway through the class. Are you starting off with activities or questions that only the top students can really engage in right away? In which case you're just sort of, you've lost everyone, and you might wonder why no one's showing up to class anymore. So when we were developing our curriculum, one other element that we tried to work in, and this came from the structure side of things, was to have an opening, engaging, contextualized question right at the beginning of class that was accessible to all students. It wasn't just the A students or the B students that could read and understand the question and perhaps provide some reasonable answer or response.
In the spirit of contextualization, the last thing that I'd like to offer is ensuring that that contextualization is not linear, that it's very, it has a racial equitable lens as well as cultural inclusiveness, because contextualizing can be one-sided as well. So ensuring that you're differentiating the context in which you're presenting the information so that all of your students are able to actually grasp the information.
Great, thank you. So again, the earlier question in terms of what you actually do, what types of content do you want your pathway to calculus to look like, to describe, to include? Here's a list of, I have 2 slides here, just eight things that we tried to work into the curriculum as much as possible. Certainly exploring ideas and concepts with multiple representations. I know this has been in the kind of the math ed lingo now for a decade or a couple of decades, but really focusing on graphs and tables and words, as well as the algebraic formulas. Those are certainly important, but to just de-emphasize that algebraic formula representation for functions, I think is really helpful. Again, this is the idea of getting back to functions or processes. They're not the algebraic formula. It's not f of x equals x squared. That tells you something. The table tells you something. Words tell you something. All that information together helps you form some mental picture of what this process is, the squaring process might be. You talked about trying to get students to move them away from just that action view of a function, and that's, getting students to describe the behavior functions on entire intervals. What's happening between 0 and 1, between 1 and 2? Maybe initially they do plug in a few points, but at some point there should be some desire and inclination just to be able to consider a whole continuum range of inputs and describe what the continuum range of outputs is going to be. When you talk about average rates of change, I think that helps move a little bit away from the action view of a process as well, because you're looking at a rate of change over an entire interval. Developing the language and inclination just to describe change, the idea of increasing and decreasing and that sort of thing. Moving towards the idea of instantaneous rate of change. Lots of practice with dynamical reasoning to help develop the student's ability to reason, to apply the covariational reasoning. Engaging curriculum, authentic STEM contexts, these all came up as obviously big pluses, and we've talked about it a lot here today already. Communication, I noticed that when Rob was putting up the skill sets this morning. Written communication usually was pretty high on his list of desirable skills. Math was a little bit further down there, and that's usually what I like to tell my students a lot. Math will get you pretty far, but you got to be able to communicate, both orally and in writing, and trying to give students the opportunity to do that as much as they can in a math classroom is really helpful. Although you can get pushback from that too. The students don't understand why they have to write in a complete sentence in a math class, but I don't know. You just got to push back against them too. Okay. Make the algebra meaningful. I think I've said that a few times today, and I'll stress it again. Try to make the algebra as meaningful as possible. Okay. It's fine and necessary to develop these procedural skills, but there's no reason it has to be done in a vacuum. What might this look like? Well, we just have a couple minutes here. I made some handouts just because this goes over a couple of slides. So here is one activity, like about a 20-25 minute activity that would show up early in a pre-calculus course. I should say early in an accelerated pre-calculus course. The curriculum we ended up designing at the Dana Center was it was a full year curriculum, but we were starting with students at the intermediate algebra stage, and then throughout the 2 semesters of classes to prepare them for calculus at the end. I know, we're about out of time. Read through, at least read through the questions. I guess we won't work through them, but read through these questions. Questions 2 on this page, and then on the back of the page is questions, I think 4 and 5 and 6. Just read through those, and then I'll say a couple words, and then we'll probably have to stop.
Just to get a little background on this, does your pre-calculus include trigonometry in it?
It does.
Okay.
Yeah. Although it hasn't come up yet when this activity has been handed out. Yeah, the idea of period, yeah. So you could think about handing this out to, say, an intermediate algebra level student. Yeah, we haven't seen sines or cosines or anything like that. We've taken a few days and we've developed the idea of a function and the notation. And that's pretty much all we're doing. And now there's a few lessons where we're just exploring what functions are all about. And so that's what this activity is, just an exploration of function, or a couple of functions that are just different than, linear or quadratic, or something you might see more traditionally early in the pre-calc course. So yeah, we're introducing some periodic functions. I flashed back up here the big 4 overarching principles that we tried to incorporate in curriculum for preparing students for calculus. I think if we had more time, we could spend 10 minutes here and dissect some of these questions to see where some of this stuff comes up. But I think you could look at some of these questions and see where we are helping to develop, anyway, this idea of the process view of a function. Okay, students are, yes, they're evaluating the function at a point or two perhaps, but they're also describing the change over intervals. Okay, and there's some questions there about average rates of change. Covariational reasoning is coming up here. Communication is coming up here. They're asked to talk about why this quantity is changing in a certain way, to explain their thoughts, to explain their reasoning. And everything is contextualized. Okay, so all the questions here are contextualized. In particular, question, I guess 6B, okay. Students are asked to take a look at that quantity, f of 6 minus f of 2 divided by 4 for 4 years. This represents an average rate of change, okay. Just for fun, just a week before coming to this conference, I just opened up the pre-calc book that we use at our institution, which is this monster of a book, which all pre-calc books have become monsters. They're over 1,500 pages or so. And again, early in the course, they developed this idea of average rate of change too. I made some copies, but I don't think I'll hand them out. The whole approach to their idea of average rate of change, they had students do lots of computations like f of x plus h minus f of x divided by h. If you've taught pre-calc, you recognize what I'm saying there. But the point is that the authors of this particular textbook made was, they said, the goal here is to eliminate the h. And they focus completely on the algebra here of your whole point here is to fiddle with all this algebra so that you end up getting these h's to cancel, and now you've mastered that idea. I don't know. There's absolutely no meaning going on there. There's no context going on there. And it's not even important. If the goal is to calculate an average rate of change, then yeah, you don't need to eliminate an h. Okay? You're not going to need to do that until you get to Calc 1, and probably only for a day and a half before you learn some derivative rules. And then you won't be doing that anymore either. So I'm about out of time, so I think I have to stop. And if you wanted to say any wrap-up words.
I just said one more thing about content. If you think about it, when you think about your calc course, it was a library of functions. You would go through the linear, and you would do the quadratic. These four can be used differently. To his question about how do you get students to develop that kind of thinking, you have to use the different representations of functions to spiral through the ideas that you talk about. So as you hit them over and over, and they're thinking about change from a table, from a graph, then from the formula, they're developing a complete view of what it is. In a sense. I think that's one of the things that I noticed. After we were done, when you kind of look at it, you're like, oh wow, we can just do a bunch of.
Yeah, even though early in this class you don't have the algebraic tools to talk about these periodic functions with sines and cosines, but that doesn't mean you shouldn't be able to talk about them. If you're only going to discuss functional behavior or relationships between quantities that vary in ways that you have the algebraic skills to play around with, yeah, you're stuck with linear, quadratic, for the first 5 weeks of your class. That can get pretty boring after a while. It's nice to look at some tougher stuff.
I know you're out of time, but I always stir the pot with this question because I teach math. And so we teach math and we apply it to other fields. When can we teach math applied to our own field?
That's a good question. And when I talk about contextualizing mathematics, or when we talk about STEM, using authentic STEM contexts to describe our activities, there is an M in STEM, and we shouldn't forget that. Not everything has to be biology and chemistry and engineering. Okay, I think it's fine to do math for math's sake. I think it's nice to see a mix of other things as well. Right. But I don't think we have to lose sight of the fact that there is an M in STEM, and we certainly don't want to do any kind of a disservice to. There are people in our pre-calc classes that are going to be math majors. There aren't many, unless you're in certain schools that have those certain programs where I don't know, 90% of your kids go on to get graduate degrees in math. But
context is also not just slide; it's also history, understanding where the ideas came from.
Sure.
That's definitely mathematical.
Yeah.
He asked that exact question when we developed that curriculum. Because you were deciding on what context to use, and he goes like, hey, there is an M in STEM. I said, yeah, there is an M in STEM. Let's have some.
Yeah. I mean, I'm a PhD mathematician. Yeah, I do math. I mean, pure math. I mean, that's my old background, and I love math for math's sake. But at the same time, I know that doing things in these more contextualized, bringing in a lot more science and engineering context, I see the eyes open up. It makes the problem more accessible because more students can just bring their own insight to the problem. People that, I don't know, can talk about rabbits and foxes. They don't have to just talk about, F and G's. Right. So I think it makes it more accessible right there. Thanks for the question.